Insane mega construction projects you must see. Bridge building and engineering documentary. The pile driving process is carried out at the south abutment of bridge file 7677 using a heavy pile driving machine. First, the pile sections are carefully positioned in their designed locations and held vertically by the pile driver's leads to ensure proper alignment. Once in place, the hammer begins delivering repeated blows to drive the pile into the ground. During the operation, the progress of the pile is continuously monitored. To determine whether the pile has reached its required design strength, engineers apply a calculation formula that takes into account the energy output of the pile driver. This formula relates the hammer energy to the penetration achieved with each blow. The pile is considered finished when the penetration per hammer blow is reduced to the specified value, indicating that sufficient bearing capacity has been achieved in the soil. In this case, the first pile sections did not reach the required bearing layer. Instead, they were driven fully into the ground without meeting the target resistance. As a result, the operation continues by adding another tile section. A new section is spliced onto the top of the installed pile, typically by welding to extend its length. The pile driving then resumes until the pile reaches the design depth and bearing capacity required for the bridge abutment. Concrete pouring begins by placing the fresh mix continuously along the length of the CO wall following the prepared form. Mixer trucks discharge concrete in a controlled sequence to maintain a steady flow and consistent quality throughout the core. The operation proceeds section by section to avoid interruptions, ensuring that the concrete remains workable and that cold joints are minimized along the cap. As the concrete is placed, workers immediately consolidate it using internal and surface vibrators. Vibration allows the mix to settle evenly within the form, fully encapsulating the reinforcing steel and eliminating trapped air pockets. This step is essential for achieving a dense, durable concrete structure capable of resisting wave impact and long-term environmental exposure. Care is taken not to over-vibrate, which could cause segregation of the aggregate or weaken the finished surface. Once the formwork is filled to the required height, the concrete surface is leveled using screeds and straight edges that run along the top of the forms. This process ensures uniform elevation and proper alignment along the entire CO wall. Any excess material is removed and low spots are filled immediately to maintain continuity and structural consistency. After leveling, finishing crews refine the surface using hand tools. The concrete is smoothed to achieve an even texture while maintaining the design slope that allows water to drain away from the CO wall. Edges are carefully shaped and compacted to reduce the risk of chipping and to improve the durability of the exposed corners. Particular attention is given to transitions between sections so that the cap appears continuous and uniform once completed. As the concrete begins to set, final finishing passes are made to correct minor imperfections and ensure a clean surface profile. Timing is critical at this stage as finishing must be completed before the concrete hardens too much, yet not too early to avoid surface defects. The goal is to produce a strong, well-bonded cap with a neat and professional appearance. Following finishing, curing measures are applied to protect the fresh concrete. The surface is kept moist using curing compounds or water to prevent rapid moisture loss. Proper curing allows the concrete to gain strength gradually, reducing shrinkage, cracking, and improving long-term performance. This is especially important in a marine environment where temperature changes, wind, and moisture can affect early-age concrete. Once curing has progressed sufficiently, the formwork is removed. The exposed concrete cap is inspected to confirm alignment, surface quality, and structural integrity. The finished cap forms a continuous protective element along the CO wall, enhancing resistance to wave action and erosion while providing a durable and stable top structure for long-term coastal protection. The demolition of the Yanda flat in Bergen was a spectacular yet carefully controlled operation. The aging residential block, which had stood for about 40 years, was dismantled with remarkable precision using a powerful demolition shear mounted on the boom of a towering 28 plane. The hydraulic shear performed the work with calculated strength rather than brute force. From a distance, the shear resembled the jaws of a prehistoric creature. Its steel teeth bit into the apartment walls, crushing concrete and cutting through reinforced structures with impressive accuracy. Instead of randomly smashing the building, the operator strategically removed load-bearing walls first. Once these critical supports were cut, entire sections of the structure collapsed on controlled stages, crashing down with a thunderous roar. Each movement was delivered, ensuring safety and efficiency throughout the process. Ronda Flat had long served as a residence for elderly citizens who spent their later years there. For many locals, the building held emotional value. However, after 4 decades, it was no longer considered functional or economically viable. The owner decided that demolition was the most practical option. This decision sparked resistance among residents of Buren-auf-Zoom, who felt it was a shame to see a solid building reduced to low. Despite public opposition, the plan proceeded as the property had fulfilled its financial purpose and was deemed fully depreciated. The demolition work was carried out by Vanium DVD, a company experienced in large-scale dismantling project. Their heavy demolition plan attacked the structure methodically. The entire project was expected to take between 10 and 12 months, since not only the visible superstructure had to be removed but also the underground foundations and supporting elements. Every part of the site required careful clearing and transport of debris. A key aspect of this demolition was sustainability. Unlike the traditional method of using a massive weapon, often described as demolition with a blunt, this project focused on precision and material recovery. Construction materials were sorted before and during dismantling to maximize recycling. Concrete, steel, and other reusable components were separated systematically. This approach reduced waste and ensured that valuable resources could be processed and reused in future construction projects. Much admiration is directed toward Jaco Van, the crane operator. From his cabin high above the ground, he controlled the shear using buttons and levers with exceptional skill. It seemed as if his fingers were directly attached to the jaws of the machine. With careful movements, he clicked exactly where the greatest structural effect could be achieved. Piece by piece, the massive building shrank, eventually collapsing into manageable piles of rubble. When the demolition is finally complete, nothing will remain but a clean construction-ready plot of land. Local residents are curious about what will replace the former Wernda plant. Many hope that the surrounding trees will be preserved as part of any future development. Demolition, though often perceived as destructive, is also a craft. Once the work is finished, something new usually rises in its place, beginning another life cycle that may last another 40 years before change comes again. In that sense, dismantling can be seen not merely as destruction, but as the first step toward renewal. The viewers witness the dramatic moments when massive ships approach the coastline or harbor and unexpectedly lose control. These vessels, weighing tens of thousands of tons, move slowly but carry enormous momentum, making any mistake during docking extremely dangerous. As the ships near the shore, strong winds, waves, or powerful currents begin to affect their stability. In some cases, sudden mechanical failures or delayed engine responses prevent the crew from reducing speed and time. Even a small miscalculation can cause the bow of the ship to drift off course, pushing the vessel directly toward the shore or harbor structures. Harbor pilots and crew members work urgently to regain control using engines, rudders, and tugboats to correct the ship's direction. However, due to the ship's immense size, these corrective actions are not always effective. The vessels may scrape along the quay, collide with break-it or run on shallow coastal areas. The sound of steel hitting concrete or rock highlights the sheer force involved in these. Despite the frightening scenes, most of these accidents do not result in serious injuries. Modern ship design and strict safety procedures help minimize damage and protect the crew. After the impact, emergency inspections are carried out to assess hull damage while towboats assist in stabilizing or reloading the ship. Stop, brother, stop. The Tema Port Expansion Project marks an unprecedented development in sub-Saharan Africa, representing the most ambitious port construction on the West African coast. Initiated by Meridian Port Services, the project has progressed through major milestones, including extensive land reclamation, breakwater construction, and the installation of advanced ship towshore and RTG cranes. With new quay walls, container yards, and modern service systems completed, the expanded port is now prepared to go live, strengthening Ghana's capacity for future maritime trade. The Primavera Camilo Sea project is a key infrastructure initiative designed to strengthen the connection between Antioquia and Colombia's Pacific coast. Led by Pavimentos Colombia SAS, the project involves building the second carriageway along the Primavera-Amiga corridor up to the Camilo Sea sector. Its scope includes 6 bridges, 2 tunnels, and approximately 5 kilometers of new roadway. Construction requires moving nearly 1 million cub-m of excavation and installing around 100 linear meters of retaining walls. A major highlight is the use of post-tensioned bridge girders, some cast in situ and others assembled externally and launched into position. The project also features long-span bridges including segments reaching up to 250 m. Additionally, the 2 tunnels pass beneath the Medellin-Cartago pipeline, demanding precise engineering. With high-performance concrete ranging from 2,500 to 6,000 psi and a dedicated supply fleet, the project stands as a strategic component of Colombia's Prosperity Roads and the Pacific 1 and Pacific 2 concessions. The Bister Bridges project is a landmark infrastructure initiative designed to support Oxfordshire County Council's vision for new housing and employment growth in the Bister area. Led collaboratively by the Council Network Rail and Story Contracting. The scheme focuses on delivering 2 new underbridge structures that unlock agricultural land to the north of the town and pave the way for the future A495 route. The project includes a reinforced concrete pedestrian underpass and a larger concrete and weathering steel highway underbridge carrying the Cheel-Turn twin-track railway line between Bister North and Banbury. Works commenced in September 2020 and followed a 7-month program of preparation, fabrication, and on-site wet pour construction. Both structures weighing a combined 100 tons were built offline to avoid disrupting rail operations. During Easter 2021, a planned 100-hour possession allowed the team to remove track, excavate 21,000 tons of earth, and carefully drive the bridges into their final positions. This successful installation, followed by extensive backfilling and track reinstatement, demonstrates a model of proactive collaboration and engineering excellence that will enhance mobility and development opportunities across Bi-Cedar. The reconstruction process for Duff's Bridge and Marley Bridge began after issues with the original tender scope resulted in an estimated contract cost of $1 million. In March 2011, all tenders were rejected. The council then engaged GHD to manage the project, including investigation, design, demolition, and construction of the two bridges. An ambitious 2-year program was outlined with a target completion date of April 2013 and a total estimated cost of $6.9 million. An options report and extensive site investigations were commenced to determine the most suitable approach. Staging was identified as a critical consideration. The decision was made to construct Duff's first so that Bow Road could service the construction of Marley, avoiding the need to use a narrow winding unsealed detour for deliveries, cranes, precast components, concrete trucks, and plant. In May 2011, 3 determining criteria, cost, functionality, and traffic impacts were used to assess options through a weighted evaluation process. 3-span, 2-lane bridges were preferred. Constructing Marley on the existing alignment saved approximately $1.4 million in approach road works. However, it required road closures. To minimize traffic disruption, Duff's was initially proposed on a new alignment downstream of the existing bridge using Super T girders. In August 2011, Cardo was awarded the detailed design contract following an open tender. During the design phase, ongoing site investigations identified an indigenous artifact along the proposed downstream alignment at Duff's, posing risks of delay and additional costs. The project team reviewed the options and decided to relocate the new alignment to the existing bridge alignment. This minimized disturbance to the riverbank and reduced the risk of impacting other potential artifacts to maintain budget and program targets. Virtually identical bridge designs were developed for both sites despite differing constraints and road geometry. Pier alignments were carefully designed to avoid the existing piers of the 5- and 6-span bridges. A variable-sized culvert span accommodated differing bridge lengths and hydrological requirements. This solution standardized demolition and construction methods, enabling innovation and efficiency. Tenders were called and the contract was awarded to Delaney Civil in April 2012, with site works commencing in June. Regional GE Technical Solutions recommended permanently cased large-diameter board piles penetrating 3 m into rock as the preferred foundation method. These board piles addressed potential scour issues from the fast-flowing Dingo Creek. 2 pile piers were positioned on either side of the existing timber decks, eliminating the need to pile through the decks and reducing safety risks associated with working near live traffic. Steel-encased concrete piles were extended to headstock level. 10-day bridge closures and the use of precast members minimized time spent in the waterway, reducing flood exposure and work at height. Site preparation included constructing crane pads, installing temporary support structures, and delivering and storing precast components. Demolition planning prioritized safety due to the unpredictable behavior of aging timber trusses. Complex engineering analysis was required to assess lifting options, as truss elements could change from tension to compression during lifting. Chaining and principal propping and strapping required engineering sign-off since Duff exceeded 16 m in height. An unrestricted demolition license was required. Due to limited space for crane setup, a 500-ton all-terrain crane was selected as the largest suitable crane. In the early morning, the bridge was closed to traffic and deck removal commenced. Each span was lifted and lowered to ground level for disassembly, reducing time working at height. Limited site area required the crane to wait while each span was dismantled before lifting the next. At Marley, improvements significantly reduced crane standby time. An innovative temporary support structure was erected beneath the timber truss span to provide stability and a safe working platform. As the 500-ton crane could not remove the truss in a single lift, the span was cut and removed in two sections with the crane configured to 350 tons. Constructing on the existing alignment provided advantages by utilizing the new piers to support the temporary steel structure. This eliminated the need for separate temporary substructure supports, reducing cost and safety risks. The new piers were designed to integrate temporary steelwork supports, minimizing potential damage during installation and removal. The standardized bridge design allowed the same steel support structure to be reused at Marley and enabled similar demolition techniques. At Marley, a 60-ton crane removed end principals and first diagonals to access new piers for steel headstock installation. Marley, at only 8 m high, required a restricted demolition license, which Delaney undertook themselves. Time-lapse footage from Duff served as a learning tool, improving planning and execution at Marley. Demolished members were quickly removed, stacked, and transported from the construction zone. Steel headstocks were installed at Duff's before bridge closure as the existing truss span sat higher than the new bridge level. At Marley, the truss deck had to be removed before headstock installation. Steel headstocks provided a cost-effective solution, spanning between piles while remaining lightweight for rapid installation. Timber trestles were carefully lowered and dismantled. Closure periods required intensive planning, risk assessments, and contingency measures. At Marley, the 500-ton crane configured with a maxi-lift guide boom system removed the entire truss span and steel support structure in one lift. The span was temporarily positioned across the river until the compound area was cleared of precast planks, allowing dismantling off the critical closure path. Minimizing closure duration was essential. Pre-stressed concrete planks with transverse post-tensioning eliminated the need for an in-situ deck, allowing immediate traffic loading. Edge planks were lifted with scaffolding attached to provide fall protection and safe access for installing transverse bars. Conduits ensured proper alignment of transverse bar holes. A second 200-ton crane lifted the far span planks from the opposite bank. Planks were positioned using hydraulic jacks against fabricated steel blocks located in headstock attachment holes. Trial assembly of precast planks was conducted in Brisbane before delivery to identify misaligned holes and prevent delays. Continuous scaffolding crews at Marley improved safety and efficiency. Abutment headstocks and curtain walls were precast for rapid installation. Casting identical planks doubled manufacturing efficiency compared to variable designs. To address durability concerns, a DSI double corrosion protection thread bar system was used for transverse post-tensioning. Pre-grouted bars in corrugated PVC sheathing with smooth outer skins provided enhanced corrosion resistance. Bars were inserted as complete units with 45 mm bearing plates and nuts. Planks were compressed with a 100-ton load before grouting joints. After 18 hours of curing, bars were fully released and retention to 350 cons. This eliminated secondary grouting and simplified construction while allowing future maintenance as multiple crews operated in confined areas. Careful site planning ensured smooth coordination. Once the compound area was cleared, the timber truss at Marley was lifted from its temporary position, completing heavy lifts. Central barrier rail sections were attached to edge planks before installation and remaining sections were pre-assembled. Fair rules for scaffolding and formwork were cast into place and capped for corrosion protection. In November 2012, Duff's Bridge reopened to traffic on the 7th day of its planned 10-day closure. At Marley, the full 10 days were required to install headstocks, complete the deck, and install guard rails. Timber spans were dismantled at ground level, allowing sound timber to be reclaimed under the Council's Sustainable Management Plan. Temporary steel support structures were designed for future reuse as emergency bridge crossings, providing sustainable benefits and cost savings. At Marley, deck drying preceded waterproof sealing and asphalt surfacing. Concurrent activities included scaffold removal, material clearing, site cleanup, and embankment reinstatement. 2 flood events in early 2013 delayed Marley's scheduled closure. However, effective project management and minimized in-water works prevented impacts on final completion date and cost. Flexible joints, guard rails, and signage were installed to complete the bridge. Marley Bridge was opened within the planned 10-day closure in April, concluding the reconstruction works. The Chenab Bridge, a marvel of modern engineering, stands as India's highest railway bridge and the world's tallest arch railway bridge. This extraordinary structure is the first in India designed to withstand contact blast loads and an earthquake of intensity 8 on the Rohr scale. Its strategic location in the young Himalayan mountains exposes it to extreme natural conditions, including gale force winds. The bridge is engineered to allow trains to safely traverse in winds of up to 90 km per hour, while sensors automatically trigger signals to stop rail traffic if wind speeds exceed safe limits. The foundation of any bridge determines its strength. And for the Chenab Bridge, constructing foundations was a formidable challenge. The Himalayan terrain posed serious technical difficulties, necessitating extensive slope stabilization before the bridge piers could be erected. The piers themselves are extraordinary. The tallest reaches a height of 137 m and rests on a massive foundation measuring 36.5 m x 50 m. The bridge spans a deep gorge with extremely steep slopes varying from 43 degrees to nearly vertical 77 degrees, making slope stabilization a Herculean task. Before construction began, elaborate geological tests were conducted to assess rock mass stability. The Indian Institute of Science in Bangalore designed the slope stabilization measures, which were subsequently reviewed and proof-checked by the international consultancy firm URS. Once the designs were finalized, preliminary site activities commenced, including tree clearing, developing dumping yards, and constructing approach roads on steep slopes to facilitate heavy-duty dumpers and other machinery. On the Buckle side, nearly 5 km of access roads were built, while the quarry side required 3 km. Catch trenches were installed at each stage to prevent excavated debris from falling into the river. Total excavation depths reached 218 m on the Buckle side and 206 m on the quarry side. Due to the extreme slope conditions, the top-down construction method was adopted to ensure safety. Initially, the topmost bench was cut and leveled, followed by staged excavation in increments of 3 to 5 m. Normal blasting was used to remove rock up to 6 m from the final profile, while precise pre-splitting involving small explosives in deep holes ensured the correct slope and prevented damage to the surrounding rock mass. Controlled blasting aided further excavation, after which excavators, jackhammers, dumpers, and dozers removed debris to designated dumping areas. Stabilizing the slopes involved installing rock bolts of various lengths 4, 8.5, and 11.5 m along with weep holes to relieve potential hydrostatic pressure. A layer of shock reedy reinforced with steel fibers was then applied to strengthen and secure the slope. On the buckle side, more than 40% of slope stabilization work has already been completed. Each construction activity follows a meticulous sequence as delays can affect subsequent tasks. Logistics are complex, requiring the transport of large quantities of diesel, explosives, and equipment to the remote site. The Chenab Bridge is no ordinary project. Its demanding design combined with the challenging Himalayan environment makes it a symbol of engineering excellence. Ufkans is proud to contribute to this landmark achievement, constructing a bridge that will safely carry trains across one of the world's most formidable landscapes, setting a new benchmark in railway bridge construction. The construction of the North Manama Causeway followed a highly coordinated sequence that combined deep foundation works, precise precast operations, and controlled segmental erection. The process began with the formation of the causeway's foundations using board cast-in-place concrete piles. Each pile was created by drilling a long shaft to the required depth and diameter, lowering a steel reinforcement cage into the hole and filling the shaft with high-strength concrete. Several piles formed a pile group which was then integrated by casting a reinforced pile cap. This pile cap acted as a rigid platform that distributed structural loads from the piers onto the piles. Once the foundation system was completed, reinforced concrete piers were built on top of each pile cap. These piers served as the vertical supports for the superstructure, providing the mounting surfaces for bearings and precast segments. Specialized bearings were then installed at the top of each pier. These components were custom engineered to allow controlled rotation, translation, and expansion of the bridge deck under thermal and structural forces. The superstructure was formed using a precast segmental balanced cantilever method. All segments were produced in a dedicated precast yard using the short line match casting technique. In this method, each wet segment was cast in a stationary mold directly against the previously cast segment to ensure perfect geometric alignment. After curing for several hours, the new segment was shifted into the match cast position and later transferred to storage. This ensured that when segments were erected on site, their joints aligned exactly. Two erection methods were used depending on location. For ramp structures, heavy crawler cranes lifted the segments into place. For the main bridge spans, a launching girder positioned each segment with precision above the piers. At each pier, the segment was lifted, aligned, and its match cast faces coated with epoxy. Temporary post-tensioning bars were installed and stressed to hold the segment during erection. Balanced cantilevering was essential. A new segment added on one side of the pier had to be matched by a corresponding segment on the opposite side to maintain structural balance. As segments accumulated, permanent post-tensioning tendons were threaded through ducts and stressed from one end of the cantilever to the other. This provided the structural continuity and strength required for long spans. When two completed cantilevers from adjacent piers approached each other, a closure joint or link slab was cast at midspan to form a continuous deck. This process was repeated across all spans until the entire bridge deck was completed. Traffic management was carried out in 9 stages. Temporary diversion roads were first constructed outside the existing Alpha Highway to allow safe access for pile pier and deck construction. Continuous quality control accompanied each stage, including concrete tests, soil compaction checks, and independent laboratory verification of materials. Environmental controls minimize noise, dust, and marine disturbance near the coast. Through this systematic sequence from piling to segmental erection and final closures, the North Manama Causeway was completed using a fast, safe and precise construction process tailored to Bahrain's coastal conditions and traffic requirements. Insane mega construction projects you must see. Bridge building and engineering documentary. The pile driving process is carried out at the south abutment of bridge file 7677 using a heavy pile driving machine. First, the pile sections are carefully positioned in their designed locations and held vertically by the pile driver's leads to ensure proper alignment. Once in place, the hammer begins delivering repeated blows to drive the pile into the ground. During the operation, the progress of the pile is continuously monitored. To determine whether the pile has reached its required design strength, engineers apply a calculation formula that takes into account the energy output of the pile driver. This formula relates the hammer energy to the penetration achieved with each blow. The pile is considered finished when the penetration per hammer blow is reduced to the specified value, indicating that sufficient bearing capacity has been achieved in the soil. In this case, the first pile sections did not reach the required bearing layer. Instead, they were driven fully into the ground without meeting the target resistance. As a result, the operation continues by adding another tile section. A new section is spliced onto the top of the installed pile, typically by welding to extend its length. The pile driving then resumes until the pile reaches the design depth and bearing capacity required for the bridge abutment. Concrete pouring begins by placing the fresh mix continuously along the length of the CO wall following the prepared form. Mixer trucks discharge concrete in a controlled sequence to maintain a steady flow and consistent quality throughout the core. The operation proceeds section by section to avoid interruptions, ensuring that the concrete remains workable and that cold joints are minimized along the cap. As the concrete is placed, workers immediately consolidate it using internal and surface vibrators. Vibration allows the mix to settle evenly within the form, fully encapsulating the reinforcing steel and eliminating trapped air pockets. This step is essential for achieving a dense, durable concrete structure capable of resisting wave impact and long-term environmental exposure. Care is taken not to over-vibrate, which could cause segregation of the aggregate or weaken the finished surface. Once the formwork is filled to the required height, the concrete surface is leveled using screeds and straight edges that run along the top of the forms. This process ensures uniform elevation and proper alignment along the entire CO wall. Any excess material is removed and low spots are filled immediately to maintain continuity and structural consistency. After leveling, finishing crews refine the surface using hand tools. The concrete is smoothed to achieve an even texture while maintaining the design slope that allows water to drain away from the CO wall. Edges are carefully shaped and compacted to reduce the risk of chipping and to improve the durability of the exposed corners. Particular attention is given to transitions between sections so that the cap appears continuous and uniform once completed. As the concrete begins to set, final finishing passes are made to correct minor imperfections and ensure a clean surface profile. Timing is critical at this stage as finishing must be completed before the concrete hardens too much, yet not too early to avoid surface defects. The goal is to produce a strong, well-bonded cap with a neat and professional appearance. Following finishing, curing measures are applied to protect the fresh concrete. The surface is kept moist using curing compounds or water to prevent rapid moisture loss. Proper curing allows the concrete to gain strength gradually, reducing shrinkage, cracking, and improving long-term performance. This is especially important in a marine environment where temperature changes, wind, and moisture can affect early-age concrete.